Welcome to the participants. This is lecture 23 on remote sensing sensors and platforms. In earlier lecture also, we were discussing about the sensor. In this lecture, in continuation, we will discuss some more polar based satellites which are quite popular around the globe, and the data is being used by large number of users for various applications. So, let us begin with this lecture. So, SPOT is another very popular satellites. It was launched by French agencies, and SPOT stands for Satellite Powered Observations de la Terre. So, this is a French term. SPOT satellites, they are sun synchronous polar satellites flying at a low altitude, and 8 degree of the inclination is there with respect to the pole. Now, if we look at the various satellites which have been launched in different period of time, the first one was launched in 1986. So, long back this was launched, and it had a additional feature as compared to the previous satellite Landsat. Then 2 was launched in 1990, 3 was launched in 1993, 4 is 1998, 5 is 2002, 6 is 2012, and SPOT 7 is 2014. So, you can see that it is also like Landsat, it is a series of the satellites, and those satellites are launched after just few years of gap, so that we can maintain the continuity. So, in fact, we several satellites were operational for that overlap period, and we used to get the data from those satellites at regular interval. So, this is the slide which shows that the journey is continuing further. So, more are planned in the near future. So, as the new satellites are launched, after few satellites, then there are changes in the sensor systems, resolution and the characteristics, and they are called a new generation satellite. So, here also in the SPOT also some changes have been made over a period of time. So, let us see the sensors. There are different sensors which have been employed, and the popular one of the panchromatic sensor, where we are getting black and white data in slightly a larger bigger wavelength region. Then XS is a very popular term which is used for multispectral data. So, we get multispectral data in different parts of the visual part of the electromagnetic spectrum. There are HRV sensors operating, and there are specifically designed sensor for mapping the vegetation cover. So, name of the sensor itself is the vegetation. So, we will take some characteristics so that we have a good background of these when we want to utilize the data from these sensors. So, SPOT 1, 2, 3, these satellites carry 2 HRV, high resolution visible sensor. This is the name of the sensor, and after SPOT 1, 2, 3, the next generation satellite, which was SPOT 4 and 5, this was planned. So, here some changes have been made, as you can see from the slide, that one additional sensor which we call as the vegetation sensor, it was added to the capability. Then these HRV sensors were providing us data in panchromatic mode and data in the multispectral mode. As we can see from the diagram itself again, that there are 2 sensors, HRV1 and HRV2, and parallelly they are covering the bigger swath. So, parallelly with the help of a small overlap, the area which is covered is much larger now onto the ground. So, swath width is much larger when simultaneously 2 sensors are scanning the earth surface. This is a high resolution visible camera which is based on the push broom system. So, if you remember, the push broom system is it has a linear array of the sensors. So, all the detectors are arranged actually in a particular line, and when the satellite is moving from north to south, the entire line swath width. So, this is a swath width. So, entire swath width is scanned in one single go. So, that way there is no rotation of the mirror kind of a thing here, though no mechanical part. So, these sensors are much better than the earlier sensors. So, push broom sensor was employed, and it was continuously along the track, it was taking the images of the ground. If we look at the configuration, further details of the sensors which were employed in 1, 2, 3, and then the lower table shows in 4 and 5. So, we were getting multispectral data in 3 spectral wavelength band, band 1, band 2 and band 3, and we were getting in addition panchromatic data. So, panchromatic data, the wavelength range was slightly longer, 0.51 to 0.73 micrometer. But what was the additional advantage here? If you remember the resolution in the Landsat, we are getting 30 meter resolution from the thematic mapper data, but here the resolution becomes much better, 20 meter pixel size. So, 20 meter by 20 meter was the pixel size in the multispectral data, and in panchromatic data it becomes further better. So, we got 10 meter by 10 meter resolution. So, these panchromatic images where we can see minute details of 10 meter size, and sometimes the smaller than that because of the background reflectance. So, these images became very popular in order to carry out thematic mapping or prepare the topographical map of the area, because the images were available to us in stereo mode as well. If we look at the specification of spot 4 and spot 5 satellites, we have multispectral bands which were band 1, band 2, band 3, and then there was one additional band which was called middle infrared band. And we know the characteristics of this middle infrared band is that it is very useful to discriminate the vegetation cover, to identify the vegetation cover from the rest of the features. And then we had the same panchromatic data. So, as far as the spatial resolution or pixel size is concerned, there was no change in the pixel size, but we had the additional band data in the spot 4 and 5 in as middle infrared band. Now, if we see what are the different kind of a data products which we got right from spot 1 to spot 7, which is providing some sensors are providing us 3 wavelength region, because 3 bands are the minimum number requirement to create a color composite. So, we got from 1, 2 and 3 we got 3 band multispectral data, but from 4, 5, 6 and 7 we got 4 band spectral data, and then panchromatic data we got at 10 meter up to spot 4, and then there was a change in the configuration, and the change was that we used to get 2.5 to 5 meter resolution, then later on spot 6 and 7 1.5 meter resolution. So, resolution became better and better as there was a progress in launching the new satellites. So, altitude roughly they are 832 elevation, but the spot 6 and 7 was launched at a slightly lower altitude, which is 694 meter. Revisit time also kept on changing. So, you can get very frequent images actually from these satellites. If we look at the satellite data, this is a color composite, I would say the true color composite, because the vegetation cover here is shown as the green. So, there is in the middle there is a river, and then there are tributaries of the river or meandering of the river. One can see there is a urban area and there is a vegetation cover. So, details one can see very clearly, because now the resolution of the data has improved and one can identify individual field. So, kind of a crop mapping or urban area mapping, these images were very useful. If we see further the panchromatic data, where spatial resolution in the beginning was 10 meter spatial resolution. So, this image which is shown here with the 10 meter panchromatic data, it contains wealth of information. In fact, if you blow it up on your computer screen using the software, then you can go up to the minute level details and can identify many features. So, people have created a thematic map and topographical map very easily at 50,000 scale using this data, because it was, you can create a stereo mode also from this. Multispectral data which was available to us at 20 meter resolution, and these are the different spectral bands. So, we could use the infrared band here, and discrimination of the different type of vegetation. So, as I mentioned that crop cover study, identification of the different type of crops, disease crops with the healthy crops. So, this was monitoring of the growth of the crop was very useful, and these images have also been used for crop yield forecasting. So, here also in the false color composite multispectral data, which is a false color composite, all the pink and the red shades are vegetation cover, and then there is a river which is showing blue color, and there is a urban setup. So, this is all bluish tint which is giving you all the urban setup in the area. So, we have a look at all the sensors which are employed right from spot 1 to spot 7. So, the second column shows that what are the sensors which have been employed, and the third column here shows the wavelength region which has been used by these sensors. So, in fact, these sensors have been designed whenever there is additional band added with a specific application in the mind, that the data would be particularly useful for a particular type of mapping, for a thematic mapping. So, we can get these images because the normal repeat period was 26 days or something, but if you have the off Nadir capability, steering capability, which I will show you next, or if you are using this satellite data from several satellites, spot satellites together, merging them together, then this repeat period becomes 3 days, something like that. Now, this satellite has additional feature and very important feature. This was a unique feature at that time, that it has a pointability feature. That means you can change the view angle of the satellite. So, normally the satellite sensor is looking downward. So, at a particular day it is looking downward, and it is covering the swath with along its path when it is moving. But when the satellite is moving in different orbits, like here it is d plus 5 after 5 days, and this is d minus 5, that means before 5 days. Before 5 days and after 5 days again also you can actually look at the same region, because you can change the view angle, and that view angle you can change up to plus minus 27 degree from the vertical. So, if you change the view angle from the vertical plus minus 27 degree, then you can actually look at the same area again. So, I want to monitor a particular area in a short period of time, just after 5 days for example. So, I can do that. I want to create a stereo model of this area. I have now this stereo two images with the overlap region. So, we can do that. So, monitoring the area, creating the stereo model, this image was very useful. So, and you know that when you create a stereo model, you can determine the elevation of the various points in the area, and ultimately those elevations can lead to either creation of a digital elevation model, or you can draw the contours in the area, or you can find the slope. So, a lot of studies are available where these images have been used to generate elevation model and contours, and then topographical mapping. So, old topographical maps were updated up to 50,000 scale very easily. The information content was available from these satellite images, and one can upgrade the contours, one can upgrade the new information which has come up. Suppose a new road has come up and there is an old map, or new urban area has come up. So, you can transfer actually on those details on the existing topographical map and update them. These are the stereo images, spot stereo images. So, you can see the left image and the right image, and there is an overlap between the two images. So, using the capabilities of that overlap, one can create a 3D model. One can use these images to identify the changes also, because they are not taken the same day, they have been taken different dates. So, there are certain features which change very fast, can also be detected from these images. This is a false color composite, and basically it is a combination of several images, because it covers a pretty large area. It is a part of the Australia which I am showing you here, and one can see that the kind of a smoke coming out So that means that forest fire is going on in this area, and one can detect the forest fire from these images very easily with the help of looking at the pattern of the smoke which is coming from the forested area. These images are available to us nowadays at different resolution. As I told you, we have 10-meter resolution, 5-meter resolution and 2.5-meter resolution. So from same satellite, but different configurations. So we can get 10-meter, 5-meter and 2.5-meter resolution data, and one can see that the area becomes smaller and smaller when we are dealing with a better resolution satellite image. So this particular area, what we see here on a 2.5-meter resolution is just here, the small part. So 10-meter is covering a larger area, but it is not that detailed. But if I look at the 2.5-meter, maybe I can see each and every building here, identify even the small house, trees, and all those small details and features I can extract from this particular data. So this is a detection of the forest fire using sequential image. We can have the image pre-fire image, like it is September 1999 image, and if we focus in the forested area, a very good color, red color, dark red color is giving, and then some kind of a fire is starting coming, and this is the smoke which is coming out in 2000 image. So having the sequential image or having the images at different time interval, that is the idea that we can detect what are the changes or disasters taking place on the earth, and then maybe we can take certain measures in order to mitigate with those disasters. There are very large number of applications of these images from the polar satellites similar to the Landsat, but here the advantage was the stereo model, the steering capability of the satellite. So you can see here that also the list is very long. We can use in land and topography, we can use these images in various agriculture application, forestry application. I have shown you the forest fire, for example, environmental protection, then water management, because you can see the small water body also from this. Change in the glacier movement can be identified. Various utilities, when we are talking of the thematic mapping or topographical mapping, we have to map all these utilities also, we have to show them, or military mission planning. So these images had varied applications, and there are large number of research publications available using this data. Then now let us talk about our own Indian remote sensing satellite, which is popularly known as IRS, Indian Remote Sensing Satellite, and this is again a series of the satellite, a large number of there starting from IRS-1A. So this was launched in, for example, in different years, different satellites, and here the name of the sensor which was used known as LIS. LIS is the linear image self scanner. So we had a linear self scanner, image self scanner, and a panchromatic data was also available at 5.8 meter resolution. So we have the data available at 23.5 meter available, we have data at 5.8 meter available, which was quite comparable to the spot data available at that time, and we had the WIFS data also, 190 meter resolution, but if we want the larger area to be covered by one single scene, we can use that. So these in IRS series of the satellite, they are launched and maintained by Indian Space Research Organization, popularly known as the ISRO, Department of Space, Bangalore. So all those satellites are commissioned and launched there itself. So let us see the characteristics of some of these satellites. Like IRS-1A, which is the first in the series, it is a polar satellite, and it was launched in 1988, March 17, 1988 it was launched. The altitude of this satellite was 904 kilometer. The inclination is given as 99 degree, that means it was making with the vertical 9 degree angle, the orbital plane. The repeativity was 22 days, that means after 22 days, 23rd day we will get the same image of the area again, which we got in the first day. Equatorial crossing time, as I told, you like other polar satellites in the morning. So it was 10:20 a.m. and 9:75 was the weight, and that is how the satellite look like, IRS-1A. So we have next in the series is IRS-1B, which was launched after 3 years. So 1991 this satellite was launched, almost the same altitude, same repeativity was taken, but we had two cameras here, LIS-1 and LIS-2 cameras. So these are the two scanners, and each was multispectral scanner, so we are getting multiple data, multispectral data from both the sensors, and we were using the capabilities of each because each has a different spatial resolution. Then IRS-1C satellite was launched in 1995. Altitude was little lower, 817 kilometer from the equator, and repeativity was 24 days, and we can actually reduce the repeativity also. Now here we had three cameras. So this is the next generation satellite where we have changed actually the sensor system. So here we have panchromatic sensor which will give us black and white data. We had LIS-3 in place of LIS-1 and LIS-2. It has been replaced by LIS-3 with a better resolution, and WIFS data. So WIFS data was giving us a slightly poor resolution but covering a very large area. So we will see the details a little later in the slide about the characteristics of these sensors. Then IRS-1D, because as I told that this is a long series of the satellite, and it was launched in 1997, and then again about the same altitude, and repeativity was 24 days, and we had similar sensors, three sensors, panchromatic, LIS-3 sensor in place of LIS-1 and LIS-2, and WIFS sensor. Then IRS-P6 was launched. So in between there were many satellites were launched for some specific purpose. As you can say that IRS-P6 was named as resource set, and we know that these satellites are very useful for natural resource mapping on the ground. So name was given resource set, looking into that aspect. So very useful for natural resource mapping. It was launched in 2003 October 17, and it has a LIS-4 camera now, again with a better resolution, and this time the resolution becomes 5.86 meter on the ground. So pixel size by 5.86 by 5.86, and it was covering a swath of, as the pixel resolution becomes better, the area becomes smaller. So it was covering only 25 kilometer swath, so 25 kilometer by 25 kilometer, and this LIS-3 camera was operating in 4 spectral wavelength region. So we were getting multiple again multi-spectral images from these resource set satellite also. There was a WIFS camera also with 80 meter resolution, and 80 meter resolution, the swath width was quite big, 1400 kilometer. So next in the series was Cartosat, and when we are preparing the map, we are drawing the line, we say the cartographic work, we are doing cartography. So the name has been derived from there itself, word cartography. So this particular satellite has been named IRS-P5 as the Cartosat 1, because again it is a series of the satellite, and it was launched in the year 2005, and the specific purpose of this was to create topographical maps at different scales. So it had a panchromatic camera with 2.5 meter resolution. So you can imagine the resolution is becoming better and better, and now the pixel size is 2.5 meter. So we can identify very small details from the data, and the swath width was 30 kilometer. So 30 kilometer by 30 kilometer was the area covered by, and now this satellite image people have used to prepare cadastral map, land boundary map, property map up to the scale of 1:5000, and making 2.5 meter contour interval from these maps, because this has the stereo capability, the panchromatic data. So these images have been used to create the topographical maps of those areas where topographical maps were not available, or update the old topographical maps or create altogether the new data. So, Survey of India, who is responsible for creating the topographical maps also, they have also adopted these high resolution satellites, IRS like Cartosat or Resources satellites, to update their maps, topographical maps which are available at different scales. So, it will reduce lot of field work when we are preparing the topographical maps at that scale. Then we have a satellite called Ocean Sat. So, ocean, for this we know that the name of the satellite indicate that the sensor was specifically designed to study the oceanography. So, the mission was to study the characteristics of the ocean, to see the aquatic environment and study the various aspects of it, and this satellite was very popular in that sense, that there was no specific satellite where we could study the characteristics of the ocean, because many of the satellites were giving us the data of the land surface only. So, this table actually now is giving us some idea of Indian remote sensing satellites. Now, we can see from this particular table here that starting from IRS 1A, 1B, P2, 1C, then P3 was launched, 1D, P4, P6 and P5. So, different years the different satellites have been launched in order to maintain the continuity. So, that continuously we will get the data, and also when the 2 satellites or the 3 satellites are working, are providing, are operating, we can provide the data in the overlap data in that particular period. Primary uses are given here. Primary uses were cartography, creating digital terrain model. So, all that panchromatic band data was available to us in stereo mode, again pointing out that particular area, changing the view angle so that we can have again the image of that area. But please remember one thing, that when you are pointing out, when you are changing the view angle of the satellite to take the image of that same area again after some time, then you are missing what is below that area from that sensor. So, you are missing the information just down below, and what you are getting is the stereo pair of that region. So, that one can use that stereo pair for creating the elevation data using the stereo photogrammetric techniques. So, lot of digital terrain models were available, because earlier the satellite images were available where we could show the information in 2 dimensional only, x and y coordinates. So, we can get the z data also. Then there were satellites which were launched for oceanography to study the physical characteristics of that, then ocean chlorophyll, vegetation assessment, snow cover study, geology and minerals, then vegetation index. So, there are several vegetation index which could be created, like ratio vegetation index or NDVI, normalized difference vegetation index. So, these images have been used to create the vegetation index and monitor the growth or monitor the vigorosity of the vegetation, density of the vegetation, the type of vegetation which is present, and further categorization of that. The IRS P4 was used for oceanography, P6 was particularly useful for agricultural applications, where we can do the carry out the discrimination of the different crops, identification, and then maybe developing some crop yield based model. Then IRS P5 was cartographic and digital elevation model. If we look at the sensor, with respect to the time, there was a change in the configuration of the sensor, and from list 1 and list 2, then we shifted to list 3 sensor, WIF center and panchromatic sensor in IRS 1C. So, 1A, 1B, they carry the similar sensor, but there was a change in 1C onwards. Then we had WIF sensor in IRS P3, and in IRS 1D we had list 2 and WIF sensor, and then there was a satellite which is called OceanSat satellite. So, there was OCM sensor. ocean color monitoring. So, color was related to many other aspects also, even to the temperature also. So, 8 bands, it was operating in 8 bands. We were getting 8 bands of data. This was very useful. Then later on the sensor, a new sensor were designed, they were called LIS 4 and LIS 3 and LIS 4, because LIS 1, 2 were already available. Then there were 2 panchromatic cameras were kept in the satellite to provide the images of the area. So, these are, this table shows how the repeat period is changing. The last column shows the repeat period from 22 days to we have come to 2 days when we are pointing out it to the same area again. The resolution of the sensor, we had for LIS 1 72.5 meter spatial resolution, and now we have come to 2.5 meter spatial resolution, or much better than that. So, as the technology is changing, as we are developing more and more number of new satellites, there is an improvement in the resolution, there is an improvement in the repeat period of the satellite. So, that means the monitoring of the resources have become much better using the capabilities of these satellites and these sensors. So, now we look at the remote sensing image which is taken from the LIS 4 sensor. This is the Mumbai city, Navi Mumbai area, and one can see, can identify in fact the circular shape of the building, and probably from the shape itself you can identify maybe this is the industrial area, this is not the urban area. So, different shapes of the buildings and different looks can give you that impression also about that particular area. Now, if you look at the application part, there are very large number of applications, probably we have listed here only few. So, as far as the resource mapping is concerned, as far as the infrastructure mapping or forest or wetland, all kind of applications have been done with the help of these images at various resolution at different scales using different data. So, if we want to cover a large area, maybe the AWIFS data has been used so that you can get a large area covered from that. There are other polar satellites as well. So, this table shows that ADEOS 1, Terra, very popular satellite, Terra Aqua, NOAA and Terra, Aster, AVHR, MODIS and Polder, they are the sensors which have been used in these, and the repeat period is also very quick now. So, we have many other satellites which are providing us the data in order to carry out the resource mapping. So, this is all about the satellites which are moving in the polar orbit. Thank you.